going to talk about the dot product, which is one of the two important products in 110C. One is called the dot product, the other one is called the cos product. So what is the dot product? In the past, we were able to add two vectors, right? We add the two vectors. How do we add two vectors? We add the two vectors component by component, right? Okay. And then we can modify a vector by scalar. So we just use the scalar to times each component of the vector, right? Now, we're going to ask this question, is it possible to modify two vectors so that their product is a useful quantity? That makes sense, right? Can you multiply two vectors? Okay, so yes, we could. Okay, actually, there are two kind of products you can multiply two vectors. Okay, one is called the dot product, which is what we're going to talk about today. The other one is called the cos product, which we're going to cover on Thursday. Okay. Now, okay. Sometimes I forgot to turn the recording on, and okay, so hopefully I can do that. Okay. All right, so what's the definition of a dot product? Okay, so the dot product, when you have two vectors, then the dot product of these two vectors is divided this way. It's a very natural way, right? Take a guess. What would that be? You just modify the components, the corresponding components, okay, and then add the sum and add them up. Okay. So the dot product is, for example, here is A1 times B1, and then adding A2 times B2, and then adding A3 times B3. That sum there is called the dot product. Okay. So the dot product is the result of modifying the corresponding components and then add them up. Okay. So what do you think about the dot product? The result of the dot product, is it going to be a vector or is it going to be a scalar, which is a real number? Shannon, what do you think? A scalar. Okay. Scalar I think any real number is scalar. Okay. It doesn't have a direction. Okay. So a vector has magnitude and also a direction. Scalar doesn't have it. This one here, you modify the component. Each component are real number. Each component is a real number. So when you modify the component, each one of them here will be a real number, and you sum up the result is a real number. It's a scalar. So it is not a vector. Okay? So it's a number. So the result here of the dot product is not a vector. It is a real number, or we call it a scalar. Okay? The dot product sometimes is called the scalar product for this reason. Okay? And sometimes we call that the linear product. Okay? Linear product. Okay? So if you heard of it somewhere else, you can, when you hear linear product, scalar product, think about that. It's the same as the dot product. Okay? Okay. So that definition for the dot product is given for three-dimensional vector, right? However, the dot product of two-dimensional vector, like this two, okay, is going to be defined in a similar fashion, right? So what is this one times dotted with this vector, this two vector? Yes?
A1 times B2 plus
A1 times B what?
B2, B1, I said.
You mean B1, okay. A1 times B1 plus what?
Plus A2 times B2.
A2 times B2, got it, good job, okay. Participation count, okay, remember, okay, great. Okay, now let's do some example just to understand this a little bit better, okay. So we're going to take the dot product of these two vector, and take a minute to work on paper on your own and tell me what do you get. Yeah, for the first one. You get 8. Let's see. 6. Try to guess again. Huh? 2? Let's check it out. Okay. I got the second one too. Okay, the first one is 2. You got it. Okay. And the second one is 6. Okay. So you multiply the component, okay, and you sum them. Okay, sum them up. Okay. So that is the second one is 6. Okay. What about the last one? Yes? You say you got 7? Okay. Melanie, right? Okay. Yeah. And then your name. And you are Jack. Yes, got it. Okay, remember now. I'll get to know your names very well pretty soon. Okay, so 7 is right. Correct. Okay, good job. Okay, so notice that the first one, this vector over here, doesn't have the I component, right? It doesn't have the X component. So that means the coefficient for the I basic factor, okay, the coefficient of that is 0. So that's why here is a 0 over here, okay? So 1 times 0. This one doesn't have the I unit factor, I basic factor, okay? All right, good job. Are you guys okay? Too busy copying down? Okay, all right, you can do it. It would be great that if you have, you can download this before class, because that way you can just fill it out. Okay, it saves you a lot of time. Okay, but don't worry, I'm gonna post this. Okay, I'm gonna make video and post it. Okay, this time maybe on my channel. Okay. Now the dot product obeys many of the laws that holds for ordinary product of real numbers. Okay, so the following are 5 properties of dot product. Okay, so for example, the first one, okay, if you have a dot of A, that is the square of this is the magnitude of the vector. Okay, so when you dotted them, okay, you get the square of the magnitude. Okay, and the second one, the dot product is commutative, which means that you can switch the order. You dot them. A dot B is the same as B dot A. Okay, and number 3 over here, the dot product is it has this kind of like the distributive property also, right? So A dot B plus C is A dot B plus A dot C. Okay, and also the next one here, if you have a scalar times this vector A and then that with B, it's the same as taking the C times the dot product of A and B, or A times the scalar C times the vector B. Okay, and the last one over here is if you use a 0, this is the 0 vector, right? It's a 0 vector. Remember, 0 vector doesn't have any direction, okay? Doesn't have any specific direction. So, and if I put an arrow on top, that means it's a vector. This one over here, it is a scalar. This one here is a 0 vector. This one here is a scalar 0. So when you have a 0 vector dotted with any vector A, the result will be the real number 0. Okay, so those are the 5 properties of dot product. Okay, now we can actually pull them. For example, we can pull the first property. The first property over here. So when we dot it to that is the vector itself. Suppose say this vector has A1, A2, A3, okay, these 3 components. When you dot it A by itself, the vector by itself, so you have A1 times A1, which is A1 squared, and then plus A2 times A2, which is A2 squared, plus A3 times A3, which is A3 squared. Well, we recognize that this is the square of the magnitude of A. Because remember, the magnitude, when we say the length of the vector A, is the square root, right? Isn't this the square root of this, right? Square root of the sum of the square of each component, right? So this one here, it is the square of the magnitude. Similarly, we can prove this distributive property of this dot product by doing this algebra here. Okay. Now the dot product, we can try to think about it. A lot of you will say, can I imagine that? Can I visualize it? Okay. Or it can be given a geometric interpretation in terms of the angle data. Okay. So over here we have the vector A. We also have this vector B. The angle between them is the angle data. Now they all start at the origin. So the vector A and B. Then A dot B. Okay. This vector dot this vector over here is the magnitude of this A times the magnitude of this B, and then times cosine data. Now, this is the thing, okay? You can prove this, okay? The data over here is an angle between 0 and pi. So the smallest one will be 0, and then the largest data will be pi. Okay, so I'm going to ask you here, if A and B are parallel vectors, then what does data equal to? Anyone? If the two vectors, the A and B. So say we have the vector A, and then the other vector B, if they're parallel. Yes, it would be 0, and also it could be pi, because one vector can go this way, right? And then the vector go the opposite way, right? So 0 or pi. Right, participation today. So keep that up. Now let's look at the second example over here. Okay. Can I ask someone to read this? Okay. Matthew, go.
If the vectors A and B have lengths 4 and 6, the angle between them is pi over b pi A times b.
Not times. A dot B. Okay, that's the dot product. Okay. By this theme here, we have A dot B equal to what? But the theme that we just talked about, do you remember that theme we just talked about?
A times b times the same thing.
Yes. Yes. The theme that we just talked about here, right? Is right here above. Okay, this is the theme here. Says A dot B is the magnitude of the two vectors times cosine data. Data is the angle between them. Okay, and data between 0 and pi. Okay, so we have this, right? Okay, now once you have this, we can calculate this dot product right here. Do we know the magnitude of this A? Magnitude of B. Those are the length, right? Okay, these two will be what? 4 and 5, 4 and 6. Okay, and what's cosine of power 3? Trigonometry, cosine power 3. 1/2. Good, very nice. Okay, 1/2. Okay. All right. So the result here is 12. Okay, you got it. Good job, you guys. Any question? All right. Am I going too fast? A little bit, right? A little bit. But you can rewatch the video again. All right. Okay, I see you stop already. Okay. The dot product, okay? Now, the formula in theme 3 also enable us to find the angle between the two vectors, right? So we have, what did we have before? So let's talk about theme 3. I'm going to copy and paste here. Okay. For theme 3 over here, we have A dot B is the magnitude of A and B times cosine data. Data is the angle between them. Okay. So now, if we want to solve for cosine data equal to, solve for cosine data, that will be what? A dot B, and then divide by the magnitude, the product of the magnitude of A and B, right? Yeah. So I know what you say. So we'll have this, okay? So cosine data equal to this. Question? So we can actually find the angle data. So once you know cosine data equal to a certain number, how do you find that data? We know data is between 0 and pi, right? So how do we get back to data? If we know cosine data equal to a certain number, you take inverse cosine to get back to data, right? So once you do the calculation to get a number, once you calculate this and get a number, you can get this data by taking the inverse cosine of whatever number you have here, right? So we can look at some example later. Okay. Now this next example, we're trying to find the angle between these two vectors over here, okay? Now, notice that what was the formula here? Let me copy that down for you. The formula here is this, right? So we have cosine data equal to this, okay? And we're trying to find the angle between these two vectors. We can use this formula, right? Okay. So in order to use this formula, the first thing we need to do is we need to find the magnitude, or we call the length of this of A and B, right? What is the magnitude of A? How do you find that? You say 3. How did you get it? You take square root of the sum of the square of each component, right? Yeah, you got it. Good. So, and what you got? You got 3? Yes, you got it. 3. Okay. And the second one, you also take the square root of the sum of each component, the square of each component. And what do you get here? You got square root of 38. Okay. All right. Now, what do we have right now? We have the magnitude of A and B. Okay. So the next thing we do is we also need to know the dot product of A and B. So then we can use this formula, right? Okay. So what's the A dot B? A dot B is you take each component, right? You multiply each corresponding component, and then you sum them up. Okay. So what's A dot B? Let's check it out. Okay. You say 2? Yeah, correct. Okay, good job. Okay. All right. So from the corollary, we have cosine data equal to. Okay, let's look at the formula. Tell me what does cosine data equal to? Equal to what? What's in the numerator is A dot B, right? What's in the denominator? Yes, the magnitude of A times the magnitude of B, right? Okay, good. You can remember that. Okay, that's nice. You understand it and then you remember, okay? Not just try to remember without understanding, okay? All right, so A dot B is 2, and the magnitude of A times magnitude of B is 3 times that, okay? So now, when you do homework on 9, this is called the exact number, okay? The one that with the square root sign is the exact number, okay? That's the exact, okay? The one with the square root sign. So, and now, when we try to find the angle between A and B, the two vectors, if we know cosine data equal to this, then what will be this data? What do? We just talk about we can take the inverse cosine, right? Okay, so we can take the inverse cosine. So in rubber side, if they ask you for the exact answer over here, that's the exact answer right here. Okay. Okay. And the next one, they will ask you find the approximation, okay? Then you can just use the calculator to approximate that, which is about 1.46 in radian or 84 degree, okay? So this is called the approximation. Okay, got it? All right. Everybody follow? Okay, good. Now, let's think about this, okay? Two lines of product, they are perpendicular or orthogonal if the angle between them here is what kind of angle when two vectors are orthogonal, perpendicular? What kind of angle? 90-degree angle, or in radian, it is pi over 2. Yes, you got it. Okay, so that will be pi over 2. Okay, so the dot product of A and B, okay, remember we just talked about theme 3, is the magnitude of A times the magnitude of B times cosine of the angle between them, right? Okay, so what is cosine of pi over 2? Cosine pi over 2 is?
0.
Good job. Okay, good job, 0. Okay, so nice. Okay, so that is 0. And 0 times anything is 0. So result here will be 0. Okay, so this tells us that if the angle between, so when two vectors are perpendicular or orthogonal, now people say, which one should I say, perpendicular or orthogonal? Now for 2D, 2 dimension, we usually call perpendicular. But then when you go to 3D or more dimension and try to say orthogonal, it sounds fancier, sounds better, okay? Orthogonal, okay? All right, so what we have to show over here is if two vectors are orthogonal, then their dot product will be equal to 0. Okay, so repeat after me. So if two vectors are orthogonal, say if two vectors are orthogonal, then their dot product equal to 0. Good job. Okay. Now, what about the converse? Okay, if the dot product equal to 0, do you think the two vectors are orthogonal? Let's check this out. Okay, so if you have A dot B equal to 0, but A dot B is equal to this, right? And if A and B are not 0 vector, then what happened here is if these two are not 0, then the only possibility is this one equal to 0, right? This one equal to 0 when data is between 0 and pi, the only angle will be pi over 2. So okay. So cosine data equal to 0. When data is between 0 and pi, data has to be pi over 2. So this just shows that the converse what we said is also true, which means that if the two vector, the dot product equal to 0, then they're orthogonal, okay? Because the angle between them is pi over 2, okay? So therefore we have the following. So we'll say two vectors are orthogonal even only if their dot product equal to 0. Now everybody say it one more time, okay? Two vectors A and B are orthogonal even only if their dot product equal to 0. Okay, remember this result. It's going to be in the quiz, okay? We test it. Okay. I have lesson concept check for each lesson. There was one due last night. I have students send our reminder like the day before, and also send a reminder yesterday to remind you. So there's no excuse, okay? Okay, but okay, if you happen to miss one or two, I think lives happen, right? Sometimes you might forget. So what I'm going to do is I'm going to drop the lowest 2 score from the lesson concept check. So if you miss just 1 or 2, just relax, okay? No worry. Don't need to contact me. Just remember, you do it next time, okay? Okay, all right, so don't forget. I will drop the notes too, okay? So also, okay, that's quite generous. All right, the next example over here, we're going to show that this vector is perpendicular to this vector in example 4. Any idea how can we prove this? How can we prove the two vectors are perpendicular, or we say they are orthogonal? How would you? Yes, we just said that, right? The two vector orthogonal even only if their dot product is equal to 0. So we can try to show that the dot product of these two equal to 0. Okay, so let's find the dot product. Okay, so how do you find the dot product? You multiply each corresponding component and sum them up, right? Okay. Did you do that? Okay. So I multiply each corresponding component, right? So 3 times 5 times -4 plus -1 times 2. Okay, do the calculation. Tell me, does it equal to 0?
Yes.
Yes, it does, right? Okay, good. So it does equal to 0. So then the conclusion over here is the two vectors are perpendicular, okay, because the dot product equal to 0. Okay. Okay, now the next question over here is trigonometry, okay, but we're basic. Okay, if theta, the angle between the two vectors, is greater or equal to 0 and less than pi over 2, cosine theta is greater than 0 or less than 0. This is at the first quadrant, right? First quadrant cosine is positive or negative. Come on. Positive, okay, positive is greater than 0, okay. All right, and then if it's theta is between power 2 to pi, cosine theta positive, negative. Negative, okay, great. Okay, so remember we just talked about the dot product, right? Okay, let me actually remind you here, the dot product. Okay, so when cosine theta is positive, then this result here will be positive, right? Okay, because the length will be always positive, or at least equal to 0, right? Okay, so, oh, by the way, that's something I also need to bring you to the attention here is the 0 vector is considered perpendicular or orthogonal to all vectors, because if we take the 0 vector and dot it with any other vector, the result will be 0, right? So the 0 vector is kind of special. It's considered to be orthogonal to all vectors, okay? So that's one. That's going to be on the quiz. Okay. Okay. So now, so we know when theta between this and this is greater than 0, between this and this is less than 0. So we can say that the dot product is positive when theta is less than pi over 2. And it is negative when theta is greater than pi over 2. Okay. And when it's pi over 2, it is equal to 0. Okay. So here is a picture. Here's a figure that can help you to see it. Okay, let's see it. So when theta is between 0 and pi over 2, okay, then the dot product is positive. When theta is pi over 2, the dot product is 0. When theta is an what do you call this angle between pi over 2 to pi? Huh? Obtuse. Okay, obtuse angle. Okay, obtuse angle. Okay, then, oh yeah, here is obtuse. Okay, then the dot product will be negative. So as you can see here, when the dot product is positive, then they kind of pointing in the same direction, right? See, point this way and then point this way, kind of pointing to the same direction, okay? And then when the dot product is 0, they are perpendicular or orthogonal, okay? And if the if the dot product is negative, okay, and they point in kind of opposite direction. See, one go this way, the other one go this way. Okay, so in general, they kind of like opposite. Okay. Okay. Same direction, that part the positive, and the converse is true. Okay, this 90-degree pivot two. When they are orthogonal, that product is 0. When they point in general opposite direction, then the dot product is negative. Okay, got it? Okay. So that product, if we're given a dot product, you kind of see if the two vectors are they pointing the same direction or opposite direction, or are they orthogonal? Okay. So in the extreme case that A and B point in exactly the same direction, we have data equal to what? 0, yes. Data equal to 0. And cosine of 0 is 1. Yes, good job. Okay. So A dot B is equal to just the product of the two magnitude, right? Okay, good. Yes. Good. What about if they point in exactly opposite directions? So what will be data? Pi, right? Yes, that will be pi. And cosine pi is -1. So this will be the opposite of the product of the two magnitude. Okay. So those are the extreme case. Same direction, but opposite direction. Okay. All right. Next, we're going to talk about direction angle and direction cosine. This is actually not required, but I'm going to just give you the information. It's just interesting to look at. Okay, okay, so the direction angle of non-zero vector are this angle here. Picture is better than 1,000 words. So look at this picture here. So this is the vector, the pink one. And alpha, this is the angle from the vector to the positive x-axis. And then beta is from the positive y-axis to this vector. And then gamma is from the positive z-axis to this vector, right? Those are called direction angles. So you have three. In 3 dimensions, you have 3 direction angles. Alpha, beta, gamma. Okay. So the cosine of this direction angle, okay, cosine alpha, cosine beta, cosine gamma, okay, are called direction cosines of the vector. Okay, direction cosine. And how do we find cosine alpha? Well, we just talked about, we had the dot product, right? We talk about that. Let me see if I can still. Remember before we had this, right? Okay. So cosine, let's see, the cosine of this angle between them is the dot product divided by the product of the magnitude. So this alpha is the angle between the vector and the x-axis. So we can dot it, the unit basic vector I, remember what is I? I is a unit vector pointing in the positive x direction. So that's I, remember? Okay. So let me do this here. Then I try to think about I. I go this way, right? And J will be pointing this, that's J. And K will be pointed this way, so that will be K, okay? So I is the unit basic factor point to the x direction, right? So cosine alpha will be A dot I times the magnitude, the product of the magnitude of this two. And we know that the magnitude of this unit basic vector is what? Is 1, right? This one here is 1. So basically, now what is A dot I? Well, how do I take this dot product? So this A over here is A1, A2, A3, right? And then we're going to dot it with this vector, the I vector. Can you tell me the 3 component for this I vector? 1, 0, 0, 1, 0, 0, okay? So when you dotted them, what happened here is only this one times this survive, because the rest over here, A2 times 0, A3 times 0 will be 0. So you will get A1. So that's why you get the A1 over here. Okay. So cosine alpha will be A1 divided by the magnitude of A. Okay, and then similarly, by similar reason, cosine beta is A2 divided by the magnitude of A, and similar for cosine gamma. Okay. Now, if you square, okay, what happens if I square? Okay, so say I square this, and then I square this and square this and sum them up. So if I square this, what do I get? If you square, that will be equal to what? A1 square over the square of the magnitude, right? And then similarly, if you square that, you get A2 square over the square of the magnitude. And when you sum them up, okay, so what happens when you sum them up? What do you think? If you square them for each one of them and sum them up, then that will be A1 square over the square of the magnitude plus A2 square, the square of the magnitude, A3 square divided by the square of the magnitude. And they have the same denominator, so we can take the common denominator, and we get A1 square, A2 square plus A3 square. My handwriting is not good. Let's sit down. Okay, but what's A1 square plus A? Huh? Oh, I put a Q here. I'm glad that you pay attention to all the detail. Okay, great. That's participation. Okay, square, yes. So, and then you realize that the numerator is just what? Is the, what's A1 square plus A2 square plus A3 square? Yeah, it's a magnitude square, right? And then divide by the magnitude square, the result will be equal to 1, right? It's equal to 1 because A here is not a zero vector, okay? So that's equal to 1. So therefore, we have this result here. So if you square cosine alpha, and then square cosine beta, and then square cosine gamma, and then we sum them up, and the result will be 1. okay? And then we can also use the two equation to write this vector, okay? So instead of, what's the equation 8 and 9? Okay, let me copy that for you. Equation 8 and 9. So here, that's equation 8 and 9, okay? So now because, okay, make it big. So A1 is, well, if you solve for A1 is the magnitude of A times cosine alpha, right? What's A2? A2 is the magnitude of A times cosine beta over here, right? Similarly that, okay? So you can actually, each component here is multiplied by the magnitude of A. So we can take out this magnitude of A because this is a scalar, okay? So take that out in front of the vector and times the vector, cosine alpha, cosine beta, cosine gamma. Now I'm going to ask you, so one way to express this vector here is you can take the magnitude of this vector, okay, times this vector here that has each component will be cosine, the direction cosine, okay, right here. Now I'm going to ask you a simple question. This vector over here, is it a unit vector? Is it a unit vector?
Yes.
Yes, the magnitude of that is equal to 1. We just prove it, right? We just prove over here, right? The magnitude is 1. So it's a unit vector. So basically so a vector A is equal to the magnitude of A times the unit vector that is in the same direction of A, which makes sense, right? Right, so direction angle and direction cosine. So therefore, if you take the vector, divide by the magnitude, you get this vector, the unit vector, okay? This unit vector is in the same direction as this A, okay? But the magnitude will be just 1, okay? Okay, now just do a simple example to find the direction angle of this vector. How do you find the direction angle? Well, which means how do you find alpha, beta, and gamma, right? So first of all, let's find the magnitude, okay? And I got square root of 14, okay? And now using this, I can find cosine alpha, beta, and gamma, okay? So can someone tell me what's cosine alpha?
14 over 92.
Yes, so it's going to be A1 over the magnitude of A. That's cosine alpha, right? Okay. So it's 1 over square root of 14. Similarly, cosine beta is 2 over square root of 14. Cosine beta is 3 over square root of 14. Okay. Now, once you know the cosine, how do we figure out the angle? We take the inverse cosine, right? So we can put the inverse cosine here, here, and then we get the angle. And notice that this one here is the exact answer here, and this one here is the approximation, okay? You guys can take a 10-minute break, okay? We come back and continue with projection. So welcome back. So we're going to talk about projection. We're going to project a vector onto another vector. So when you take a look at this figure over here, you see that we have this vector B and then this vector A over here. And then they have the same initial point P over here. Now, when you project this vector B onto this vector A, and so you draw a line that will be perpendicular to this vector A, and then we intersect over here. So from the tip of this vector, you draw a perpendicular line. And then this is called the foot. What happened over here is this PS over here, starting from P and pointing to S over here, is called the vector projection of B onto A. And we denote it this way. This is the notation. So project is a vector projection of B onto A. Okay. So when you project the vector B onto A, then again you will get a vector. The vector will start from here and point at here. Now, an easy way to think about this is you can think about it as a shadow. Think about this vector here, cast a shadow on this vector in the direction of this vector, and that's the shadow of this vector in this direction. So vector projection of B onto A has this notation, and you can think about that vector here as the shadow of this vector onto this in this direction. Okay. Now sometimes B and A, sometimes the angle between them will be greater than power 2. Then the shadow will go this way, right, in the opposite direction as this vector A. So this projection will go this way. Again, you can maybe this easy way to think about is the shadow. Okay, it's a shadow of this B in the A direction. Okay, and it is a vector. The scalar projection, the one we just talked about, it was the vector projection, right? The scalar projection basically is just the magnitude of it. Okay, so this vector casts a shadow on this vector A, right? And then you can just focus on the magnitude, the length of this. That's the scalar projection. And that is, well, we know how to find the magnitude of this, right? This is the right triangle. This is the hypotenuse. The length of this is the hypotenuse, right? And this is theta. To find this adjacent side, then you will have the magnitude of this times cosine theta to get this, right? So the scalar projection of this vector onto A is the magnitude of B times cosine theta. Okay, this one here is a scalar. It has no direction. It's just the magnitude of it. And how is this one related to the vector projection? Well, this is the magnitude of the vector projection. Okay, this is how long it is. And then the vector projection will have the direction. So point this way, point that way. Question about this too? So the scalar projection, okay, remember the scalar projection is it's a scalar, right? And it's think about that as the length of the shadow. Okay, how long is this shadow? We denote it this way. Is com of B onto A. How did the com here come from? The COMP there come from the component of B along A. So what is the component of this B along this A? Well, in physics, they do that a lot, right? Think about this as a force. What is the component of this force along this direction? You use the magnitude of this force times cosine theta to get the component of this force in this direction, right? Okay, so COMP stands for component. Okay, so component of B along A, and this is the notation for that. Component of B along A. It is a scalar projection. Okay, it's a number. It's the length of this shadow. Okay, so component of B along A. Think about it as the length of the shadow. And if this angle theta here is between 0 and power 2, it should be positive, right? In the same direction. Okay. So it should be positive. Okay. And if theta is between power 2 and pi, then cosine data will be negative, then what happened here is then we have a negative number. Okay, so when B is pointing in general opposite direction as this A, right? When the data is greater than power 2 and less than or equal to pi, so you will have, for example, you can have the B like this, okay? And when you have B like this, then the angle data will be this. Then that will be from power 2 to pi, and cosine of that angle data will be negative. So therefore, the component of B along A, well, let's try to visualize how does it look like. It looks like this. Show this. Then this is the one. This is the component of B along A. When B points this way, A points this way. So A and B will point to in general opposite direction. Okay. Okay, this equation. Now over and over, we talk about that product. A dot B is the product of the magnitude times cosine of the angle between them, right? So, and now this one over here is exactly what we have over here. It is the component of B along A. So we can also think about that product of A and B as the length of A times the scalar projection of B onto A. Okay, so when you do that product, okay, so when you have A dot B, then what do? You can take the magnitude of A and times, then you think about if you cast the shadow of this B onto A, how long would that be? And then you just times the length of the shadow. Okay, so A, the magnitude of A times the shadow of B, that will give you the dot product. So A times the scalar projection of B onto A, which is, think about it as a shadow, the length of the shadow. Okay, so the component of B along A, you can compute that. So because of that, right? Because the formula we have for dot product, right? So we can actually, this one over here is the component. This is a component of B along A. So you can take this dot product and then divide by the magnitude of A to get that, right? But then you can group these two together. So A divided by the magnitude of A, this one here just gives you the unit vector in the A direction. So basically is the unit vector of A dotted with B. So another way to think about this shadow, the length of the shadow, is you can think about this as the length of the shadow. You can think about, what's the length of this shadow? You can think about that as taking this B, take this B, and then dot it with a unit vector in this A direction. So think about, this is B, right? And think about how long is the shadow it casts. Then you dot it with the unit vector in this A direction. Okay? So think about it as the length of the shadow. It's the length of the shadow along this A. Okay, projection. Now we're going to summarize and put these two together and compare and contrast them. And first one is the scalar projection of B onto A. We'll talk about that. Is going to be equal to this. Okay, think about that as the shadow, the length of the shadow. Without here is the real number. This one here is the projection. It's a vector projection of B onto A. Think about that. It's the shadow itself. This is the length of the shadow. This is the shadow itself. So that's equal to this. Okay. So you see the relation between these two over here is the vector projection is the scalar projection times the unit vector in the direction of A. So, well, which makes sense, right? Because this is the length of the shadow. You just take the length of the shadow times the direction of the shadow, right? This is the direction of the shadow in the A direction, right? Okay. Okay, it takes some time to get used to all those notations. So be patient with yourself and sit down and think about it, okay? Right. Now let's look at one example. Find the scalar projection and vector projection of this onto this vector. Any ideas? Let's do the scalar projection. How do you do that? What do I need first? What's the formula for scalar projection? Right, scalar projection, right, is the length of the shadow, right? So you take this B, the length of B, and then what? Times what? Cosine theta, right? Okay, let's do that. Okay. So we find the length of A first, right? Okay. And then we also find the, okay. So what do we do here? Okay, so we find the length of A, okay, and then we try to find the scalar projection of B onto A, which means the length of, try to find the length of the shadow, okay. Then what do we do here is we're going to, remember how do we do that? We can take the dot product, right? So we can take the dot product. Well, let's try the formula one more time just to remember this. So what was the dot product formula? Okay. So A dotted with B, because all of this come from this formula. If you remember that, you have no trouble, right? A dot B is equal to the magnitude of A times the magnitude of B, and then times what? Cosine of theta. Okay, so remember that one. Try to also remember what was this, okay? So what is the component? What was the component of B onto this vector A? What does it equal to? You don't remember? That is equal to, that's equal to the magnitude of B and then times what? Cosine of theta, right? Okay. And what was the projection? And then the projection of that is just take this component and then dot it with the unit vector of A, right? Okay, let's put it down over here. So what will be the projection of B onto A? What would that be? Equal to, so that will be just the component. Just take the component of B onto A. Remember, this is kind of like the length of the shadow, but then you still need the direction. So you multiply this by the unit vector in the A direction. So you can take the A divided by its magnitude, then you get the projection, right? Okay, so those are the three formula to remember. Well, it doesn't hurt to write it down alongside, so then just remind you, okay? Now, if I want to find this one over here, I will try to find the magnitude B times cosine theta, but over here, we're not giving the data. We don't know the angle between them, right? But then from here, you see, we can actually solve for this, right? Can we solve for that? We can solve for this, right? We can solve for that one. And when we solve for this, that's equal to the dot product divided by the magnitude of A. Okay, so therefore I can find the dot product, I can find magnitude of A, I will figure this out. Okay, so the first thing to do here is I find the magnitude of A, and then I find the dot product, and then I will just use the dot product divided by the magnitude of A to find this out, right? Now, how do you find, so just think about it as the length of the shadow. And then the vector projection is basically the shadow itself, okay? It has direction, okay? So it's a scalar projection times the unit vector in the direction of A. So you just take this result, take the length of the shadow, and then multiply by what? How do you find the unit vector in the direction of A? you just take A, divide by the magnitude of A, right? So take A, divide by magnitude of A, that will give you direction. So, and we know the magnitude of A is square root of 14. So multiply this two together is 14. So that's how you got this 14 over here. So 3 over 14 times the vector A. And we know this vector A here is given. So you can just go ahead and use 3 over 14 to distribute and multiply each component of A, and that will be the vector. Okay, so this is the shadow, and this is how long is the shadow. Okay, got it? A couple new concepts today, but it takes a while to get used to it. Okay, finally, okay, now it's something related to physics. Okay, in physics, the work done by a constant force in moving an object through a distance d is work equal to 4 times distance, right? 4 times the displacement, right? Okay, but this applies only when the force is directed along the line of motion of the object. So which means, for example, like this, so you have this, and then you have this object over here, right? And then the force is going to go the same direction, and then moving a distance of d, then work is equal to 4 times the distance, right? 4 times the distance. Okay, so now suppose that the force, okay, the constant force over here, the force here is a constant, okay? Suppose this constant force here is going this way, but the object moving this way, right? That happen, right? When I pull my
suitcase here.
So I pulled it this way, but then it goes forward, right? Okay. So suppose the force goes this way. So in this direction over here. Do you understand?
Now here's my suitcase.
The force I'm pulling this is going this way, right? Along this handle. Okay. But this is moving along the floor. So the force over here is not in the same direction as the way that this one moves. So that's the example. Okay, this is the force. And it is a constant force. Okay. And the way that this one moves is along this one, along the floor right here. So how can I figure out what's the work done by this force along this direction? Let's think about it. So if we move this object from this point P to this point Q, okay, then the displacement vector will be PQ. So from here to here, okay, let's call that vector D, okay, and we need to find the component of this force along this direction, right? Along the direction that this object moves. What is the component of this force along this direction? How do we find out? If this is the length of this, right? So if we can find how much is this force, and we know this angle, how can I find the component of this force along this direction? Yes, you got it. It's the magnitude of F times cosine theta, right? I think last time we talked about the tension, one student also remember that, right? So it's the magnitude of that times the cosine of theta that will give you this component right here. So when you decompose this force in this component, and in this direction, you get this component, okay? So that will be the magnitude of this force times cosine theta. And then think about this is the force along this direction. And then times the displacement. The displacement is the magnitude of this d, okay? From P to Q, the magnitude. So magnitude d. So put this together and change the order. You can put this as the magnitude of F times the magnitude of D times cosine theta, which is exactly the dot product, right? Isn't it the dot product of F and D, right? F is the force vector, D is the displacement vector. When you dotted them, you get the work done. So that product related to physics is, in this case, is the work done. So the work done by exerting this force on this object, move along this direction, is this F vector, the force vector dotted with this displacement vector D. Got it? Okay. There's a little bit physics here. Okay. Okay. This example over here. So a wagon, hey, I wanted someone to read this. Okay. Can I ask Shannon to read this? Here.
The wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 7 newtons. The handle of the wagon is held at an angle of R of 35 degrees above the horizontal, find the work done by the force.
Good job. Okay. All right. So this wagon is pulled a distance of 100 meters. So think about it as kind of like this, 100 meters along this horizontal path. And so along this path right here. And the force here is a constant, which is 70 Newton. Okay, 70 Newton. Okay. And the handle of the wagon is held at an angle of 35 degrees above this horizontal. Find the work done by the force. So the F here is the force vector, D is the displacement vector, okay? Then the work done will be the dot product of these two. Okay, so we're going to take the dot product of these two. Then how do you find the dot product? According to the definition, dot product, it is what? It is the magnitude of F times the magnitude of D times cosine of the angle between the F and the D, right? Okay, what's the magnitude of F? 70 Newton, right? Yeah, good. What's the magnitude of D? What's this 100 meter? Yes, good job, okay? So we substitute. So this is 70 Newton. This is 100 meter. This cosine 35 degree. So we did the calculation and turned out to be 5,734 Newton times meter. And Newton times meter, in another way to express this unit is joule, right? A joule. So that's the result. So that's how much work is done by pulling this wagon 100 meter along this horizontal direction and with a constant force of 70 Newton. And that's the end of the dot product. Do you guys feel okay with it?